Okay, yeah, right. I hope you're well. This video is just going to take you through the Block 2 test you just did, and we're going to kind of have a look at some of the questions that people struggled with, try and explain what the answers were and how we got there. I'm not going to go through every question. You can see from this graph, there are certain questions where you appear quite confident. What I'll do is I'll focus on these ones where there were quite a number of students who struggled. So we won't do number 1, and I might just keep coming back to this graph, but we will do number 2. So we've got question number 2. And this one's about a reaction with acids. So Ben put a beaker weighing 50 grams on a balance. He added 50 grams of dilute hydrochloric acid and 2.5 grams. Yeah, so we've got total mass there. How could Ben tell a chemical reaction was taking place in the beaker? Well, I think the obvious thing here is fizzing. Then we have a word equation. Some water had evaporated, and that's why it dropped in mass. What else caused the drop in mass? Production of a gas, because what will happen is the gas will leave the beaker. Some people think like gases don't weigh anything, but actually carbon dioxide is quite a heavy gas. If you filled a balloon with carbon dioxide, it wouldn't float away, it would actually sink to the floor. When the reaction stopped, Ben tested the contents of the beaker with a universal indicator. The calcium carbonate had neutralised the acid. That's going to be a fairly easy one. That's green. The next one's a pretty hard one. I don't know if we've ever covered this. We've certainly covered some of it. So which two materials are mainly calcium carbonate? Well, we've done about limestone recently, and that's calcium carbonate. And then, if you know that one, you can work out the second one, which is marble. Because marble is a metamorphic rock and it is made from limestone. And then this is just a question going back to the reactivity series topic. So metal plus acid gives salt and hydrogen. So that's question number 2. Question number 3 and 4 seemed fine. Question number 5, which is about starch digestion, that's one we will go through. Right, yeah. So this is a pretty tough question, but it's also quite similar to a practical we did. So we've got saliva digesting the starch, or more particularly amylase in the saliva. We've got these Viscin tubing bags, which are made from a semi-permeable membrane. So smaller materials can pass through, smaller molecules, larger ones cannot. And she's got 3 experiments. So this one has starch and saliva. This one just has starch, and this one just has saliva. She keeps them at 37 degrees, that's human body temperature, and then she tests them after 20 minutes. So what we're seeing is, was starch found and was sugar found? Both in the bag and in the water. Firstly, you keep the water at 37 degrees to increase the rate of reaction, and it's human body temperature. So if you've got saliva, it will work best at human body temperature. That's what it's designed to do. Explain why sugar was found in the bag in beaker A. Right, so we've got starch and saliva. So what's happening here is the saliva is breaking down the starch, and the product of that is sugar. Starch was not found outside, not found in the water outside the bag in any beaker, suggests why. And that's because starch is too large to fit through the semi-permeable membrane. The only things that can pass through a semi-permeable membrane are small molecules like sugar or salt. Starch is lots and lots of sugar molecules joined together, so it's far too large. Why did Sally set up beaker C? So beaker C is just saliva, there's not actually any chemical in there. So we'd call that a control. A control's designed to observe if there's any results when you don't have, say, an active ingredient. So in this case we don't have any starch, we only have saliva, so we won't expect anything to happen, but it's just to check that. If we suddenly discovered it tested for starch and it appeared black, then we'd have to go back and reconsider all our results. Then we've got some diagrams. Okay, so we've got P, Q, R and S, and we've got starch as the large molecules, sugar as the small molecules. So it says, use the diagrams above to answer the following questions. Which diagram shows the result of beaker B? Right, so beaker B had just starch, so that would be P. There's only starch in there. It stays in the bag, it doesn't go in the water. Which diagram shows the results of beaker A? Now beaker A had starch and it had sugar. And if we have a look at the results, we get starch in the bag, sugar in the bag, and sugar in the water. So starch in the bag, sugar in the bag, sugar in the water, so the rest of it. What does saliva contain that causes starch change in beaker A? We could call it enzyme, more particularly it's the enzyme amylase. Sally is weird. She chewed a piece of bread for about 5 minutes without swallowing. What would she notice? I mean, you can actually try this if you're bored and unable to go out. The bread actually starts to taste sweet. It's not particularly nice sweet, but you definitely notice it. Probably after, not quite after 5 minutes, after about 30 seconds of chewing, as long as you don't swallow it, so it starts to turn sweet. Question 6, 7 and 8 are also ones that we're going to have a look at. So question 6 is all about rocks. So we've got a mountain range, and it says choose the correct letter from the diagram to best match the descriptions below. You may write each letter more than once. So, rock changed by heat and pressure. Well, if we'll have a look at our key, okay, metamorphic rocks are those changed by heat and pressure. Rock formed by magma cooling and solidifying. Well, that's the dark grey one, that's D, because that's how igneous rocks formed. The oldest rock would be the one that is lowest down. Probably. That's how we see. Region where eroded materials are deposited. Well, eroded materials are things like sand and mud, so that would be A. And a region not affected by erosion, so we've just got to choose something that is not exposed to wind and rain. So I think that's only going to be C. And then we get our different types of weathering. So we've got physical weathering, which is a process of force that damages rocks or breaks up rocks. And then we've got chemical weathering, which is a chemical. So an example of physical would be freeze-thaw. I'm not going to write this down, but we could describe it. So freeze-thaw, water gets into cracks in rocks, freezes, expands, and breaks the rock open. And then our usual one for chemical weathering, that's acid rain. And what we'd say is acid reacts with the rocks, probably producing a salt and a gas. 7 we'll go through as well. So 7 was about reactivity series. I think that was maybe the first topic we did or the second topic we did in year 8. So a lot of this is about displacement. So we've got molten iron for railway tracks is produced by the reaction between powdered aluminium and iron oxide. This is the thermic reaction, which I think I showed you. I'm sure I will have done. So it's a displacement reaction. So what happens is the more reactive metal, which is aluminium, displaces iron from its oxide, so we're left with iron and aluminium oxide. Iron can be produced from a mixture of aluminium and iron oxide, but not from a mixture of copper and iron oxide. Write down the names of the three metals in the order of their reactivity. So aluminium must be the most reactive. Iron is the next most reactive, and then finally we have copper. We've got some other metals then, displayed in terms of their reactivity. What, if anything, would be the result of heating zinc powder with calcium oxide? Well, zinc powder is less reactive than calcium, and calcium's already bonded to the oxide, so the zinc wouldn't be able to displace this, so there won't be a reaction. I don't think it wants an explanation, but I'm putting an explanation in for you. Write down the name of the metal in the list that will not react with this solution of magnesium sulfate. So we want something that's less reactive than magnesium, so I'm going to choose silver. The powdered metal with the symbol Zn, why they just can't call it zinc, burns in air. Write the word equation for the reaction. So zinc plus oxygen. So that's when metal reacts in air, it's already reacting with the oxygen, and that will form zinc oxide. Right, and I understand why so many people have put question 8. Was question 8 the most common one? Yes. Question 8 is a hard question. It's actually a GCSE question that we put in the Year 8 exam. We've probably done a kind of a maybe similar experiment. You'll have probably done it in Year 7. That's the only problem. And you won't have done the exact experiment. So this requires quite a lot of thinking, quite a lot of working out. But if you've got good science skills, you should be able to get some marks. So firstly, it gives us a bit of background. We'll spend a bit of time on this question. Exothermic reactions transfer energy to the surroundings. The surroundings increase in temperature. You'll have done that in Year 8, and one of the surroundings is a thermometer. Then we've got the chemicals given to a student and the equipment for undertaking an experiment. So we've got 4 different metals. Dilute sulfuric acid, we've got a measuring cylinder, what looks to be a thermometer, and a beaker, and wants to investigate the reactivity of the 4 metals. We've got to give a plan, and the plan should use the fact that all 4 metals react exothermically with dilute sulfuric acid. And we've got to name the apparatus used and comment on the safe use of chemicals. So I would start this one by thinking about my variables. You don't necessarily get marks for this, but it really helps you to plan it. So my independent variable is going to be the metals. Crucially, my dependent variable is going to be to do with this. So they all react exothermically with dilute sulfuric acid. So the thing I could measure is the change in temperature before and after the reaction. So I'll measure the temperature of the acid at the start, add in the metal, and then measure the temperature of the acid after the experiment to get the change in temperature. And then also I want to think about control variables. So mass of metal, volume of acid, concentration of acid. And they would probably be the main ones. Maybe the starting temperature of the acid as well. Type of acid as well. And if you control those things, then the only thing that will be affecting the change of temperature is the metal that you're using. So you want to get all these 6 things here into your method. So what I'd probably do is start off by saying, I always do methods as a series of points. So measure 2 grams of metal W. It doesn't matter that 2 grams might not be a sensible value, might not be what scientists use, as long as it's a given value, there's no problem with that, and it's not ridiculous. 2 grams is quite small. It's not going to flow over the beaker or anything. And then we'll measure 50 millilitres or centimetres cubed of 1 molar dilute sulfuric acid. So now I've covered mass of metal, concentration of acid, type of acid, and volume of acid. Measure the temperature of the acid for the reaction, and then add the metal to the acid, stir once. Now I've just noticed I missed something, so I've not really been talking about the apparatus, so I'm just going to go back and add that in. Measure 2 grams of metal W with a balance. Measure 50 millilitres of 1 molar dilute sulfuric acid using a measuring cylinder. And this is kind of the importance of reading the question, because otherwise I would have missed some marks. Measure temperature of the acid before the reaction with a thermometer. Add the metal to the acid, stir once with a glass rod or a stirring rod. Wait until the temperature increases and then starts to go down again. And actually we should hear. We should start the stop clock then. Stop the stop clock. Stop the stop clock. That doesn't sound very good, does it? Yeah, I can't think of anything else. Stop the timer when the acid reaches its maximum temperature. What you don't want is to do it after 10 seconds or 20 seconds or too long. You want to let it go as high as it will and then come down, and you want to record the maximum. And then what I would do, and I always try and do this when I'm writing methods, is to explain about the importance of repeats. So repeat twice more with the same metal, and calculate a mean. And we could exclude anomalous results, which are results that are a bit away from the other results at that point, and then we repeat with the other. Repeat the method with the other metals. Right, and then if we go back, have we outlined a plan? Yeah. We've named the apparatus used. We haven't commented on the safe use of chemicals. So then we can just write for safety. Where safety clauses. That would probably be the main thing for this experiment. Another thing you could do is have the reaction beaker in the centre of the desk, so it's not near an edge. Okay, and I think the last 2 questions were actually. Oh, sorry, there's another part of question 8. So we get a lot of information then about metals W, X, Y, and Z and how they react with different chemicals. It doesn't matter that you really don't know too much about these chemicals. What we can conclude though is the order of reactivity. So I'd start here because sulfuric acid, it's easy. We're ending metal Z is obviously very unreactive. We can probably just put that straight at the bottom. Z. X is quite unreactive because we're only getting a few bubbles of gas. So we can put that there. And then we've got two where we can't distinguish, Y and W. If we look at other ones as well, we're not getting any change there, so it's really hard to distinguish between them. So then if we have a look at the last one, well, if the metal's more reactive than zinc, what would happen is it'd remove the zinc from the chloride, and then the zinc would be displaced and would get a grey layer of zinc. So what we can conclude is that metal W is the most reactive, and then we'll go for metal Y. You would then explain that in those sentences. Okay, and I think that's it. Thank you for watching. I'll put the instructions for what you do next on the Teams page.